Alright, hello everybody. Welcome to this new video in a course on orthogonal polynomials. The purpose of this video is to prove the so-called three-term recurrence relation for orthogonal polynomials. And we're going to do that using Gram-Schmidt procedure. But before we do that, let me first of all tell you what that relation is, and then tell you how this relation is important to relate the theory of continued fractions to the theory of orthogonal polynomials. So the statement that we want to prove is that if we start with a sequence of orthogonal polynomials, Pn, then we have the property that we have this property. Okay, we have this equation, and some people like to rewrite it or to write it in a different way. You can write Pn plus 1 at x is equal to x minus Bn times Pn of x plus An minus 1 times Pn minus 1 of x. So we have this relation, and that's pretty fascinating. We're going to prove it. We're going to see how to prove it. The proof isn't that bad. But before we do that, let me first of all give you an example and then show you how we can connect this to continued fractions. So, we spoke of Chebyshev polynomials. In fact, Chebyshev polynomials are going to satisfy the following relation. They're going to satisfy the relation x t sub n of x is equal to half t sub n plus 1 of x plus 0 times tn of x plus half times t sub n minus 1 of x. So the sequence Tn is the sequence of Chebyshev polynomials that we spoke about in the previous video. These are the orthogonal polynomials with respect to the weight function 1 over square root of 1 minus x squared. And they satisfy this three-term recurrence relation. And I want to change this a little bit and write it as a continued fraction. And here's what I'm going to do. So what we can do is we can, first of all, multiply by 2 and rearrange the terms. So we can rewrite things as such. Tn plus 1 of x is equal to 2x times Tn of x minus Tn minus 1 of x. The reason we have this thing is because of this theorem that we're going to prove. We're going to prove in full generality, and the reason we have these coefficients or these terms showing up here is because of these coefficients that we have a general form of, and you can compute these and you can indeed get that. So what I'm going to do now is that I'm going to divide by t sub n. So I'm going to divide by that, and I have Tn plus 1 over Tn of x. And that's going to be equal to 2x minus Tn minus 1 of x over Tn of x. And now notice that we can do something here. And what we can do is the following. We can look at the reciprocal of that, and we can write it as such. So if we take the reciprocal, that's going to be 1 over 2x minus Tn minus 1 of x over Tn of x. But notice that this thingy here, so notice that this thingy here, it's just this one, but n is replaced with n minus 1. So in other words, I can use the fact that this is going to be in this form, except that n should be replaced with n minus 1. In other words, this is going to be 1 over 2x minus 1 over 2x minus tn minus 2 over tn minus 1 at x. And we can iterate this process, and what we get is that this ratio is going to be just 1 over 2x minus 1 over 2x. So let me write it more neatly. 1 over 2x minus 1 over 2x, and we're going to have a sort of a ladder here going all the way. It's going to stop. So let me write it in this way. Dot 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 minus 1 over 2x. So interestingly, you could write this like ratio of these orthogonal polynomials as like as a continued fraction, and there's a lot of connection going on here, but we're gonna probably get to that later, but I figured that I should mention this. So yeah, so from this 3-term recurrence relation, for example, you can immediately see some connection with continued fractions. Okay, now leaving that aside, let's go ahead and prove this theorem. But to prove this theorem, we need like I need to remind you of the so-called Gram-Schmidt procedure. So let me remind you of that quickly, and if you want more details, you can refer to my video. I have a video explaining this process in details. So recall how the Gram-Schmidt process works. What we're gonna do is we're gonna start with in this case n+1 vectors, and we're gonna assume that these vectors are linearly independent. Then the Gram-Schmidt procedure allows us to turn these into n+1 orthonormal vectors, right? And by orthonormal we mean, so here we're assuming that the vector space is equipped with an inner product, and by orthonormal we mean exactly that Ej is gonna be 0 if I is not j, and it's gonna be 1 if I is j. And recall we can do that simply in this way. What we can do is we can first of all normalize the first vector, normalize it in this way by dividing by the norm. So here we're speaking of, you can think we're speaking of the two norms. So here the norm is just u0, and then you take square root. Okay. And then what we're gonna do is we're gonna introduce new vectors uk's. So at step k, at step 0, we're gonna normalize the first vector. At step k, we're gonna assume that we already have found E0 up till ek minus 1. So we're gonna do it by induction, and we're gonna introduce the kth vector uk to be the vk vector that we already have, minus the projection of that vector onto ej for every j less than k minus 1. Okay, so the details are left to you, and you can check my video. I'm gonna leave a link to it in the description. But this is the process, and this is how we can introduce the orthonormal list. And at the end, like when we introduce the UK, we normalize it just as we did in step 0. So this procedure, I'm gonna assume that you're familiar with it. If you're not familiar with it, maybe it's a good idea to stop the video, go watch the video in the description, and then come back. But otherwise, we're gonna continue with the proof. Okay. So what's the idea here? We want to prove the theorem, but before that, let me remind you quickly of what it means for two functions or two polynomials in our case to be orthogonal with respect to a weight function w. It means that we want the inner product of these to be 0, right? So we can if we restrict ourselves to the space of continuous functions on -1, 1, we can define the inner product of fg as such, as an integral of this function. And if it is 0, we're gonna call f and g orthogonal. Okay, so this implies f and g are orthogonal. Okay, so from now till the end of the video, when I use this notation, I mean I'm doing this. This is the inner product. And when I say orthogonal polynomials, I mean that this inner product of them is 0. Okay. So now, okay, so let's go ahead and prove that. And I probably have a typo here. Sorry about that. The observation here is the following. What's happening is that I'm gonna rewrite it in a slightly different way. So I'm gonna rewrite this as such: minus pn of x minus an minus 1 pn minus 1 of x. Okay, so the observation is that it looks like we're constructing pn by taking a polynomial of degree, we're constructing pn plus 1 by taking a polynomial of degree n plus 1 and subtracting from it the projection of it on other polynomials. So it looks like this is resembling what's happening in Gram-Schmidt here. And as I mentioned here, just to be fully correct here, this is provable in the case when pn's harmonic and the norm of pn is 1. Okay, so we're just adding these little assumptions. You can get rid of them and prove something similar, but just these make the proof cleaner. So I'm gonna assume these. Okay, and now let's see how to use Gram-Schmidt to easily get this fact. Okay, so let's go ahead and do that. Okay, and now we're gonna bring the Gram-Schmidt process into the picture. So the point is, starting from p0 up till n minus 1, we can construct an orthogonal polynomial to each and every one of these. Okay, and that polynomial has to be pn. The reason it has to be pn is because of the assumptions that we've put on the pn's, right? We've made sure that these harmonic polynomials of norm 1 to ensure uniqueness. So the assumptions we've put on the pn's ensure that whenever I'm gonna introduce a new orthogonal polynomial to this space that has the same properties, it's the only orthogonal polynomial. So it's gonna be it has to be pn, right? But then we observe that pn can be constructed in this way. What we can do is we can take this polynomial of degree n, so this is of degree n, and then what we can do is we can apply the Gram-Schmidt procedure to this to make it to get an orthogonal polynomial to all the pk's. So we can subtract the projection just as we do in Gram-Schmidt. We can subtract the projection onto each and every pk, and we get a pn. Okay, we get, let me call it a pn tilde tilde. Okay, we get some Pn. So this function, it's orthogonal. This polynomial, it's of degree n to begin with. It's monic in the sense that its coefficient, its higher order coefficient has is just 1, right? So the coefficient of x to the n is 1. This is what it means to be monic. And it's orthogonal to all the pk's, and it can be shown that it has norm 1 by looking at the inner product of it with itself, and this forces it to be Pn itself by uniqueness of orthogonalization. So this is Pn itself for sure. And now what we've done is that we've rewritten Pn in this way. But this is almost what we need because it suffices to prove that most of these terms here vanish to get the three-term recurrence relation that we're looking for. So let's see how we can get that. And what we have to use here is that we have to use the orthogonality, because notice here we have some inner product. And whenever we talk of orthogonality, we expect that the inner product of some polynomials to be 0, right? And we can easily see here, I mean, by definition, notice if we have x times f inner product it with g, this is the integral of xf times g times w of x dx. But I can put the x near g, and thus this is the same as f inner product it with g. In other words, it's you can observe that this term here, it's just Pn minus 1 inner product it with x times pk, like that. And what's interesting about this is that we already know that Pn minus 1, it's orthogonal to every polynomial of degree less than n minus 1. Okay, so Pn minus 1, it's of degree n minus 1, and hence it's orthogonal to every polynomial of degree less than n minus 1, because it comes from this orthogonal set, right? And particularly, whenever this has degree less than n minus 1, then this will be 0, right? So this is 0 so this happens whenever the degree of xpk is less than n minus 1. But the degree of xpk is 1 degree higher than the degree of pk, because pk is monic. So this is the same thing as saying that the degree of pk is less than n minus 2. But the degree of pk is just k. Okay? And thus, almost all of these terms disappear, because almost all of them are zeros, right? In other words, what we have is that Pn of x is just x Pn minus 1 of x minus, I'm gonna start from the biggest k and I'm gonna go down. So at k equals n minus 1, we have this. And then at k equals n minus 2, so notice as long as we're not less than n minus 2, these terms need not be 0, okay? Then we have the n minus 2th term, so x Pn minus 1 times Pn, inner product this with Pn minus 2 times Pn minus 2, and the rest of the terms are just zeros, right? The rest of the terms will have k less than n minus 2, and hence all of them will be zeros. And we precisely get what we were looking for. This is the three-term recurrence relation, if you put instead of n plus 1 everywhere in this relation, you get exactly what we were looking for. So if we want to show you the details or the cleaned up version, this is what we have. So if you just replace n by n plus 1 in the last equation, we exactly get what we were looking for. We exactly get this.